So let's take a look at how we would use functional notation. Here we have a function, and this reads g of x is equal to negative x squared plus 2x minus 1. And we want to find the following values. Now, when we see this notation here, g of negative 2, basically it means that we go to the g function, or the function whose name is g, that's this guy, and then we're going to plug in whatever the x value is that is indicated inside here. This is telling me that we're going to be plugging in x is equal to negative 2. And then after we plug in x is equal to negative 2 in the function, we're going to determine who is the corresponding y value. That's a lot of words, right? Go to the g function, plug in x is equal to negative 2, and determine the corresponding y value output. That all of that can be said in a much more compact notation that is just g evaluated at negative 2 or g at negative 2. So this is quite the shorthand, right? So this notation is shorthand for all of this stuff. So let's do it. So we are to go to the g function and plug in x is equal to negative 2. Well, anytime I plug something in for x, I like opening up holes to receive whatever it is that I'm going to be plugging in. And in this case, since we're plugging in x is equal to negative 2, as is indicated in the functional notation, negative 2 is going into both of those spots. And so we'll say g at negative 2 is on the left here. Now, PEMDAS, or please excuse my dear Aunt Sally, says that exponents have to go first, so I'm going to say negative 2 squared is positive 4, but then this negative is going to have to wait. So negative 2 squared is positive 4, and then this negative comes down to be multiplied by positive 4, so it's going to end up being negative. And then we have minus 4 from this product, and then minus 1. So g evaluated at negative 2 is going to be negative 9. And so what this tells me is that when x is equal to negative 2 that we plug in, the corresponding y value output that comes out is going to be negative 9. So let's do that again for a couple of more examples. We have now g at 4. So if I have an x inside the functional notation, I'll have x's out here in my equation. But if I have a 4 inside that functional notation, that means I'm going to be plugging in 4 into those x spots. So we'll say 4 gets plugged in for all the x's in the function. So now we will copy paste the left hand side. This is g at 4 that we're finding. We've got negative 4 squared, which is negative 16, plus 8 minus 1, and therefore g at 4 turns out to be negative 16 plus 8 is negative 8 minus 1 is again negative 9. And what this means is that when we plug in the x value 4, we get out the corresponding y value negative 9. And with functions, remember, it's okay to have two different x values generating the same y. We just can't have one x value generating two different y's. And if we were to think about this in an ordered pair kind of a situation, remember, an equation is a collection of ordered pair solutions. So the ordered pair that we would get from this first scenario is that the x-coordinate is negative 2 and the y-coordinate is 9. And the ordered pair that we would get from this second scenario is that when x is equal to 4, we also get a y value of negative 9. So we have two different x values generating the same y, and that's okay in a function. Last example, we're looking at g evaluated at x plus 1 this time. Again, I'm just going to recopy our original function, which is g of x is equal to negative x squared plus 2x minus 1. And with functional notation, if I have x inside here, then my x's are going to be in that independent variable spot in the equation. But if I have x plus 1 inside here, then I'm going to be plugging x plus 1 into those variable spots. So whatever is indicated in that functional notation is what gets plugged into those independent variable spots. So here we go. We're going to rewrite the function, but with holes this time, because whenever we're changing what is being plugged into the independent variable, we start off by opening up a receiver hole. And then if we have x plus 1 inside here, then x plus 1 is what's going to go inside both of those independent variable spots. So again, we copy paste our left-hand side so that each step of the way is algebraically equivalent to the previous step, and all we can really do here is to simplify. We will do this by FOILing out this binomial and then distributing the 2 into the parenthesis. So let's begin. This negative has to wait because please excuse my dear Aunt Sally or PEMDAS says that the square has to go first. And we can't distribute a square over add, so we have to FOIL that. And that means that this product inside here is going to be square the first, which is x squared. The product is 1 times x, that's just x. Twice the product is 2x, and then square the second. So FOILing this binomial is going to give us x squared plus 2x plus 1. And then let's go ahead and distribute that 2 into the parens over here so that we have 2x plus 2 minus 1. And then now we are ready to distribute the negative in. And that's going to give us here, let's again copy paste the left hand side down, negative x squared minus 2x minus 1, and then copy pasting these things, 2x, let's go ahead and call this plus 1 because we are going to be combining like terms in the next step to get it as simple as possible. So we have negative x squared minus 2x plus 2x, those two things are going to cancel out.
And minus 1 plus 1 also cancel out.
So we end up with g evaluated at x plus 1 is going to give us the output that is
just negative x squared.
If we have a variable expression that we are plugging in, we're going to get a variable expression as the output.